using greedy approach. So in continuation with the greedy methods, today I'm going to make a discussion on another type of problem which can be solved using greedy method. So the problem is called as job sequencing with deadlines. Job sequencing with deadlines. So you're very much familiar with what is called as job scheduling. So, or processor scheduling, CPU scheduling algorithms, like first come, first serve, shortest job first, round robin algorithms, right? So you have studied all these CPU scheduling algorithms in your operating systems subject. So you know that you'll be given a set of processes. There will be a single processor. All these processes have to be executed on the processor. So whenever a job, a process has to be executed, it needs to be allocated some processor time. So for that, you'll perform scheduling. If there are n number of processes in the queue, you'll use some technique, maybe first come, first serve, where whichever process has entered the queue first, it will be first executed, then the second job will be executed, and so on. Or you may go with shortest job first. Among all the processes that are ready in the queue, you'll first execute the process whichever has shortest time, shortest execution time. So all this is what is called as job scheduling. So this job sequencing with deadlines is also a similar problem. And we'll try to schedule the jobs in such a way that maximum profit is earned. So this is the definition of the problem. You'll be given n jobs to be processed on a machine. And the jobs are represented as J1, J2, J3, and so on up to Jn. So you have been given n number of jobs that are ready in the queue that to be executed. And these are the constraints. Only one machine is available for executing the jobs. At a time, only one job can be executed at a time on the machine. And to execute a job, 1 unit of time must be spared. One job will take 1 unit of time to get executed. As such, you can execute only one job at a time. And only one machine is available for executing the jobs. Now, each job is given a deadline and it is associated with a profit. So if I take job number I, it has a deadline DI, and this DI deadline is nothing but the time period before which JI must be completed. So say, for example, I have some job number J1 whose deadline D1 is equal to 3. D1 is equal to 3 for job 1. That indicates that J1 must finish its completion before third time unit. So you have, for example, time units like this. You have time number 1, time unit number 2, time unit number 3. And if deadline for job 1 is 3, that means J1 must be finished before the third time unit. This is the maximum time period that is available for completion of J1. After that, you need not complete the job. Before third unit, you have to complete job 1. And if this constraint is satisfied, that J1 execution is completed before third time unit, then you are going to earn a profit, PI. So for job 1, there will be a deadline. And if job 1 is completed its execution before this deadline, then you'll be able to earn the profit. The profit may be 2 or some number, some integer number. Okay, so each JI will be associated with a deadline and it will be associated with a profit. And profit is earned if the job is completed before its deadline. Okay, and now what is the solution for this? How does the solution for this problem look like? Given a job sequencing with deadlines problem and you apply greedy approach, the solution will be an ordered subset of jobs. It may look like this. It's a solution vector, a job vector. J2, J3, J5. This may be your solution, for example. And now this solution vector of jobs will be a subset of the jobs that have been given. So you have been given n number of jobs. You have been given n number of jobs. And this solution will be a subset of n number of jobs. And it's ordered subset. That means there is a particular order. Here the order is J2, J3, J5. That means that on the machine, first time unit, J2 will be executed. In the second time unit, J3 will be executed. And in the next time unit, J5 will be executed. Only these 3 jobs will be executed among n number of jobs. It need not be compulsory J2, J3, J5. It may be J3, J5, J2. This may be the solution vector. That means on the machine, in the first time unit, J3 will be executed. In the second time unit, J5 will be executed. In the third time unit, J2 will be executed. So 3 jobs will be completed before their given deadlines. Hence, I am going to earn a profit through this. I am going to earn a profit of P3 because J3 is completed within its deadline. So its profit will be earned by me, which is P3. J5 is also completed within its deadline. So its profit will also be earned. Then J2 is also completed. So I have also earned profit too. So with this job sequencing, J3, J5, J2, I have earned the profit of P3 plus P5 plus P2. That's the total profit earned with this job sequencing. Now, how to develop this sequence of jobs? How to develop the solution for a given problem? Now, I'll try to define for this particular problem, what is a feasible solution and what is an optimal solution. So a feasible solution for a job sequencing problem is a subset of jobs such that each job is completed within its deadline. So I have J2, J3, J5. This is a solution. Now this solution is a feasible solution if all the jobs J2, J3, J5 are finished before their given deadlines. So as such, there may be many feasible solutions for a given problem. And within all such feasible solutions, one solution or one or more solutions may be optimal solutions. And an optimal solution is a feasible solution that will give you the maximum profit. And how you calculate profit for a given solution, it is equal to the sum of the profits for all the jobs in the solution vector. The profit for a solution is the sum of profits of all the jobs in a given solution. If that particular solution is earning you a maximum profit, then such a feasible solution is called as optimal solution. And again, as I have said in the previous session, greedy approaches are of two types: subset paradigm and an ordering paradigm. Now we are discussing problems that fits into subset paradigm. What kinds of problems fit into this subset paradigm? So as such, we are going to identify a subset of jobs. From given n number of jobs, you are going to identify a subset of the jobs. So the solution is identification of a subset. Hence, you are going to apply greedy approach, which is called as subset paradigm. So I'm going to discuss a sample problem for job sequencing. So consider the following instance of job sequencing problem, where the number of jobs are equal to 4, and there are profits and deadlines given for the job. P1, P2, P3, P4 are the profits of the 4 jobs: J1, J2, J3, and J4. D1, D2, D3, D4 are the deadlines for the jobs. Now, profit P1 is 100 and the deadline is 2. That indicates that if job J1 is scheduled and it is completed before second time unit, then its profit of 100 will be earned. Now job J2 has a profit of 10 and a deadline of 1. That means job J2 must be completed before first time unit, then you will be able to earn the profit of 10. So as such, I have 4 jobs which have to be completed in these given deadlines. Okay, so now defining the problem. The problem is job sequencing with deadlines for the given set of jobs. And the constraint, jobs must be finished before their deadlines so as to earn the profit. Now the objective function is to maximize the profit earned by job sequencing. That means you have to schedule the jobs in such an order that you are going to earn maximum profit. Now that is your challenge, and for that you are going to apply greedy approach. So I have tabulated the given problem here, where the number of jobs are 4. For each job, I have given a name: J1, J2, J3, and J4. For each job, there is a profit and there is a deadline. Now I have reordered these jobs. Actually, the jobs given are J1, J2, J3, and J4. But now I have reordered the jobs as per their profits in the decreasing order of profit. So J1 has highest profit of 100, then J4 is the next highest profit, 27, J3 15, J2 and 10. So I have reordered the jobs as per their decreasing order of profits, from maximum profitable job to least profitable job. Now I'll have to schedule. There might be different possibilities of schedules. Right? Now, can I schedule all the jobs? That's the first factor you have to determine. Can I schedule all the 4 jobs for completion and on all the 4 profits? Is it possible? So for that, you'll have to check the deadlines of the jobs. For job 1, deadline is 2. For job 4, it is 1. Job 3, it is 2. For job 2, it is 1. So I have the deadlines as 2, 1, 2, 1. So there is a job 2 and another job 4. Both have to be finished within the first time unit, which is not possible. I cannot complete 2 jobs in a single time unit because you have to remember all the constraints. I have only one machine available for execution. One time unit will be required for executing one job. Then I can execute only one job at a time. So if I remember all these constraints, then it's easy for me to observe that out of J2 and J4, I can complete only one job. Any one job I can take and I can complete. Then out of J1 and J3, again, which have to be completed before second time unit, I can complete only one. So that means whenever you have been given a set of deadlines, find out what is the maximum deadline. So you can see that the maximum deadline here is 2. So check out maximum deadline, and if it's 2, that means that you can schedule only 2 jobs. Isn't it? I can finish only 2 jobs within the given 2 time units. That's the max. Now what can I do? I have 2 time units. That means I can complete only 2 jobs. Then which 2 jobs will I select for completion? It's my natural instinct that whichever jobs will give me maximum profit, I'll finish those 2 jobs. So these 2 are the jobs, J1 and J4 are the 2 jobs that I'll naturally select for completion so that I can earn the maximum profit. So how does this process go? So it's simple that there might be many feasible solutions. If you start filling up, there will be many feasible solutions. A feasible solution is the one where the jobs are finished before their deadlines. Okay, so if I take this 9th solution, I'm going to execute only one job, which is J4. This solution is a feasible solution if this job J4 is completed before its deadline. The deadline for J4 is 1. If J4 can be finished within first time unit, then its profit will be earned. What is its profit? 27. So this is the profit of the solution. Take the first solution where I'm going to execute 2 jobs. I'm going to execute job 1 and job 2, both of them. But in this particular order, I'm going to execute J2 first, then I'm going to execute J1. So you can see here, because among J2 and J1, J2 has to be finished before first time unit, within first time unit. J1 can be finished within 2 time units. So I'm going to first complete J2, then I'm going to complete J1. Both of them are being finished within their deadlines. So it is a feasible solution. Now, what is the profit earned? It is profit of J2 plus profit of J1, which is 110. So you might go for many such solutions. 9 feasible solutions are possible here. And these are the profits earned. Now, my objective function is to schedule the jobs in such a manner that maximum profit is earned. So among this, all these profits, you can see that this is the maximum profit, 127. And for achieving 127 profit, you have to execute job 4 and then job 1. This is the sequence. First, you are going to execute job 4, then execute job 1. You are going to get a maximum profit of 127. So now among all these feasible solutions, the third solution is in optimal solution, that is giving me the maximum profit. Now, how did I know that I have to complete job 4 and job 1? So these are the 2 jobs that are to be selected to earn the maximum profit. So for that, I have here, that is why we have reordered the jobs in the decreasing order of profits. Now the process goes like this. Check the deadline, maximum deadline value, which is 2. The maximum deadline value is 2. That means I can finish 2 jobs within 2 time units. That is the limit. I'll have to select any 2 jobs. So naturally, what will I select? I'll select the first 2 jobs. If possible, it might not be possible at all. Sometimes it might not be possible to complete the jobs with the highest profit. So in this scenario, I'm going to select J1 and J4. So I'll start drawing a Gantt chart. I'm going to draw a Gantt chart. You already know how to draw a Gantt chart. So you'll have a grid of cells, grid cells. It's a vector. This is the first time unit. This is the second time unit. And I'll have to fill which job will be executed in first time unit, which job will be executed in the second time unit. I'll start filling. So I'll take the job that gives me the highest profit, J1, and its deadline is 2. That means it has to be finished within either first time unit or second time unit. So I'll put it for execution in first time unit. Done. Now I have one more time unit. I can execute one more job. Now I am going to select the job J4, which gives me the second highest profit, 27. J4 I am going to select. Now, can I write J4 here? Is it possible that I execute J4 in time unit 2? Is it possible? No, it's not possible because deadline for J4 is 1. You can see the deadline for J4, which is 1. So it has to be finished before the first time unit. So if I'm completing it in the second time unit, that means I'm not satisfying the constraint. The constraint is J4 must be finished within first time unit. So if I am not satisfying the constraint, then J1 comma J4 is not a feasible solution. If a solution is to be feasible, then I'll have to satisfy all the constraints. So what I'm going to do is I'm going to reorder. I'm going to put J4 here and I'm going to put J1 here. This will be the order of scheduling. I'll finish first job and fourth job, but the order of processing is J4 comma J1. If I put the order like this, then I'm satisfying the constraints. J4 is completed. J4 is completed within first time unit. J1 is completed before second time unit. So this is a feasible solution. And if this feasible solution is giving me the maximum profit, then it will become an optimal solution. So what is the total profit earned for this schedule J4, J1? It is profit of J4 plus profit of J1, 27 plus 100, which is 127. Now, whether this is optimal solution or not, that may be optimal solution, it may not be optimal solution, because the greedy approach itself may produce less optimal solutions, because at each step it makes locally optimal choices. So it may produce globally optimal solution, it may not produce globally optimal solution. Okay, so the optimization measure or the selection procedure. The optimization measure here is the sum of the total profits of the jobs. And the selection procedure is based upon the optimization measure. That means at each step, I'm going to select a job which gives me the highest profit. That is my selection procedure. So whatever the process that I have discussed till now, The process step by step can be tabulated, something like this. There are 5 columns. What is the job number? What is the slot, time unit slot? What is the solution? What is the profit earned till now? And what is the status? So first I'm going to select step 1. As per the selection procedure, you have to select the job that gives you highest profit. So J1 will be selected. It will be scheduled to be completed in slot number 0 to 1. It is time unit 1. Till now, the solution vector consists of job 1, and the profit earned by executing job 1 will be 100, and the status of job 1's execution will be processed. Then step 2, again, among the remaining jobs, I'll select the job which gives me highest profit. So I'm going to select J4. This time slots are 0 to 1 and 1 to 2. The order of processing the jobs is J4, then J1. The total profit earned till now is 127, 100 plus 27. And the status of J4 is processed. Now I'll try to fit some more jobs. Can I complete some more jobs? J3, right? I cannot complete J3 because J3 has to be finished within 2 time units. First 2 time units. Already first 2 time units are occupied. If J3 has to be scheduled, J3 has to be scheduled in the next time unit. That is, I can schedule it in the 3rd time unit. I can schedule J3 here. Then if I schedule J3 in 3rd time unit, it is violating the constraint. J3 is not being completed before its deadline. So I cannot schedule J3 in 3rd time unit. So J3 will not get processed. I cannot schedule it. So J3 is not processed. So the time slots, the solution vector and the profit will remain same. And the same situation is also applicable for job J2. So this is the final solution vector for the given instance of the problem. And this is the total profit earned. This is an J4, J1 is an optimal solution produced by applying the greedy approach. Now, this is a high-level description of greedy algorithm for the job sequencing problem. So I have devised an algorithm. The algorithm's name is greedy job. It takes 3 parameters, D, J, and N, where D is the set of deadlines, J is the set of jobs, N is the number of jobs, total number of jobs. And the set of jobs J must be ordered in non-increasing order of their profits. Now I am going to start. The algorithm starts by initializing the solution vector J with job number 1, because the jobs are already ordered in the non-increasing order of their profits. So naturally, the first job in the queue will have the highest profit. So anyway, I'm going to select the job with the highest profit mandatorily. So the first job will be added to the solution vector. remaining jobs from second job to nth job, you'll have to find out whether you can include this job into the solution or not. Now I'll start with second job. I'll try to check whether second job can be included in the solution or not. So for that, I'll have to find out whether this second job can be included in the solution. Ith job can be included in the solution if after including all the jobs can be completed before their deadlines. I'll repeat, if ith job is included into the solution vector, then all the jobs in the new solution must be completed before their deadlines. If that is the situation, then include ith job into the solution vector. Otherwise, you will not add ith job into the solution. And this will be repeated from the second job to the nth job until you are going to come up with a final solution that gives me the highest profit. So this is the higher level abstraction of the greedy algorithm. Now, if I drop down into the details on how can I find that after including I to the current solution, the solution is still feasible or it is not feasible. That's the first challenge. Then second challenge, if I decide that ith job is included into the solution, then into which time unit I have to place this I. That is also has to be decided. There are two things that have to be decided, whether I have to include ith job into the solution or not. Then I have to decide into which time unit I have to fit this ith job. So for that, we have this algorithm, the algorithm with low level of detailing, which will actually decide whether ith job must be included into the solution or not. If ith job has to be included, then into which time slot this I has to be fitted. So for this, I'm going to work out a simple problem. Check out this instance of the job sequencing problem. You have been given 6 jobs, J1 to J6. Each job is associated with the profit and deadline. And you can observe that the jobs are ordered as per their profits. The job with the highest profit to the job with the lowest profit. So there is already an ordering. Now, if I have to decide how many number of jobs I can complete within their deadlines, so for that, I have to find out the maximum deadline value. So you can see here, there are deadlines 3, 1, 4, 2, 3, and 3. The maximum value of the deadline is 4. That means that I can complete any 4 jobs out of 6 jobs. Now, which 4 jobs I'll have to complete and what will be the order? Let us try to decide. So I'll start drawing the Gantt chart. So the Gantt chart has 4 time units. Time unit number 1, 2, 3, and 4, into which I can schedule any 4 jobs. Now, the first job in the order gives me the highest profit that will be mandatorily selected. So J1 is mandatory. For now, I am going to place it into first time unit, but I can also place it into second time unit or third time unit because deadline for J1 is 3. So I'll have to finish it before third time unit, 3 time units, first 3 time units. So I can put J1 here, I can put J1 here, or I can put J1 here. But for the purpose of computing, I have to write an algorithm. So always I'll put J1 into first time slot, whichever is free. Then I'll try to move it here and there as per the requirement. Now, I'll have to choose the next job. So naturally, I'll choose J2, which is giving me the second highest profit, 50. And its deadline is 1. Now, where do I have to place it for execution? Now, can I place J2 here? No, I cannot place J2 here because its deadline will be violated. Its deadline is 1. So it has to be mandatorily completed within first time unit. But first time unit is already occupied. So what I can do, now I have to check whether J1 can be moved to the right side. Can I move J1 from first time unit to the next time unit? Yes, for that, you have to check the deadline of J1. Yes, it's possible. I can move J1 from here to here, right? So J1, I'm going to move it from here to here. Then this place will become empty. I'll schedule J2 here. Okay, so now the schedule will look like this. Now, next job that I can schedule, I'll pick J3 because it's giving me the third highest profit, 35, and its deadline is 4. Now, where can I schedule J3? I can schedule J3 here. I don't have to move J2 or J1. I can schedule J3 in the third time unit because its deadline is 4. Okay, so now after scheduling, your Gantt chart will look like this. Now I'm going to select J4. J4's deadline is 2. Now, if I write J4, schedule J4 here, then it will not be a feasible solution because a constraint is being violated. J4 must be finished within deadline 2. So I'll have to reorder. Now, what can I do? For that, I'll have to check whether, can I move J3 to the right side? Yes, it's possible that I can move J3 to the right side. So what is going to happen? Here, J3 will come into the fourth time unit. It's possible that I can move J3 to the right side. Yes. Now, J1, can I move it to the right side? Yes, J1's deadline is 3. So I can move J1 to the right side. So J1 is coming here in the third time unit. Now, second time unit is becoming free. So I can put J4 here in the second time unit and J2 will remain in the first time unit. So what is this order of the jobs? The order of the jobs is J2, J4, J1 and J3. Now check whether is this a feasible solution. Yes, it's a feasible solution. For all the jobs, their deadlines are being satisfied. It's a feasible solution. Okay, now what are we doing here? Actually, whenever a job has to be included into the time slot, I'm going to reorder the jobs as per the requirement. I may have to reorder the jobs. So for that, how to reorder? For that, you have been given some conditions in the algorithm. Through checking these conditions, you are going to decide the ordering of the jobs. So if you see the previous example, I have decided that J4 cannot be scheduled into 4th time slot because the deadline of J4 is 2. Then I'll start to move the jobs to the right side. J3 is moved to the right side. Then J1 is moved to the right side. J2 is not moved. J2 is kept as it is. Then within the empty slot that appeared here, I have fitted J4. Now how I'm going to decide that J3 can be moved to the right side or it cannot be moved? J1 can be moved to the right side or not? J2 can be moved to the right side or not? So for that, these are the conditions. You have to repeat this process until you find an empty slot to fit J4. If you find an empty slot to fit J4, you'll fit it. Sometimes in some scenarios, you'll not find an empty slot to fit J4. Then you'll not be able to execute J4. You'll not be able to schedule the J4. So here you can see that I'm checking the condition. J4, what is the deadline of J4? J4 is the one that needs to be scheduled. J3 is already there in the array. So J2, J1, J3 are already there in the array. J4 has to be fitted somewhere. So this is the job J4 to be scheduled. J3 is already scheduled. Now I have to decide whether J3 can be moved to the right side in the array. So for that, I have to check the deadline of J3 and compare it with the deadline of J4. Deadline of J3 must be greater than or equal to the J4, and deadline of J3 should not be equal to R, where R is the number of jobs that are already there in the queue. So if these two conditions are satisfied, if these two conditions are true, then J3 can be moved to the right side. That is, currently J3 is in 3rd time slot. It can be moved right side to the 4th slot. It's possible. So J3 here was in 3rd time slot. I have moved it to the 4th time slot. Now again, repeat. Now J1 is here. Can I move it to the right side? Now again, you have to check. You have to decrement R value and you have to again check the conditions. Deadline of J1, is it greater than or equal to deadline of J4? And deadline of J1 must not be equal to R. If these two conditions are satisfied, J1 can be moved to the right side. Currently, it is in 2nd time slot. I'm going to move it into 3rd time slot. Now there is a gap here. Now I have to decide whether J2 can be moved to the right side. For that, again, I'm going to decrement the R value and check the deadline of J2, compare it with J4. And deadline of J2 should not be equal to R. You can see that these two conditions are false. So if any one of these conditions becomes false, then you are going to stop the process of reordering the jobs. So 1 is greater than or equal to 2. No, the condition is false. 1 is not equal to 1. No, the condition is false. Both the conditions are false. If the conditions are false, that means J2 cannot be moved to the right side. This is inevitable because the deadline of J2 is 1. It has to be finished within the first time unit. I cannot move it on to the right side. So now here is the empty slot for J4. Now I have to decide whether I can place J4 here or not. I can schedule J4 here or not. So J4's deadline is 2. J4's deadline is 2. So I can place J4 here. I can schedule. If, for example, J4's deadline instead of 2 if its deadline is 1, for example. J4's deadline is 1. So even though there is an empty slot here, I cannot schedule J4 here because that will be violating the deadline of J4. So after all this analysis, I have to decide whether whichever empty slot is available, whether I can schedule J4 or I cannot schedule J4. If J4 can be scheduled, then it's fine. If J4 cannot be scheduled, then I'll move on and repeat the entire process for seeing whether J5 can be scheduled. Okay, so for this entire process that is discussed, this is the algorithm. Don't fear, the algorithm looks like this, but it's very simple. This is the job scheduling algorithm, which will take the deadlines, which will take the jobs and the number of jobs. These three will be the parameters for the algorithm. So D is the deadlines. You already know D of I is an array which consists of number of deadlines. Then the jobs are ordered in a non-increasing order. So profit of first job will be greater than the profit of second job and so on. Then J of I, J is the solution vector that you have to prepare. So J will be the optimal solution that you have to calculate. Okay, so for now, I'll include first job into the solution vector. Then from the second job to the nth job, you have to decide whether you can include the job into the solution or not. For that, this is the process. You can see here the process that just now I have discussed, or you are going to initialize it with 1, which indicates the number of jobs that are already there in the solution. Then you have to repeat this process. You have to check these two conditions. Deadline of J of R should be greater than deadline of the ith job, and deadline of rth job should not be equal to R. If these two conditions are true, decrement the R value and repeat the process. Once any one of these conditions becomes false, you're going to stop and you'll have an empty slot. You might not have an empty slot. So that will be decided. Your ith job can be inserted at a position which is R plus 1. So you'll have this loop repeated and some value you'll have with R. And you can insert ith job into the solution at position R plus 1. Ith job is inserted into the empty slot. Now, ith job, can it be inserted into the empty slot or not? That also you have to decide. For that, you are going to check these two conditions. And if these two conditions are true, you are going to insert ith job into the empty slot. Otherwise, you will not insert. And to create an empty slot, this is this loop for moving the entire array to the right side. So here you can see that we have moved all the entire array to the right side. So J3 is moved to the right side. J1 is moved to the right side. So up to some point, some rth position, this is the rth position, up to which this entire sequence of jobs will be moved to the right side by 1 step. So for this movement, this is the loop for moving the entire queue, entire array to the right side by 1 step. Then after moving, you'll have an empty slot at R plus 1th location, and at this empty location, you are going to include the ith job. Okay, so this is your greedy algorithm for job sequencing with deadlines. And the time complexity of this algorithm is big O of n square. So for each